Hello and welcome to today's physics lecture, wherein we shall be understanding that what would be the value of magnetic flux density on the coaxial line due to a bar magnet, right? So for this, let us say draw the diagram that this is a bar magnet, right? And over here there is the North Pole and this is the South Pole. Now the North Pole will be having, say for example, the pole strength as equal to small m, and likewise the South Pole of that very same magnet will be having the pole strength equal to m. Right? Now it may be noted that a bar magnet is basically like a magnetic dipole, because this has got equal but opposite pole strength. Why opposite pole strength? Because say for example we keep a point over here, this point, and say for example this is the North Pole, right? And if we assume this is the North Pole, this North Pole will actually repel each other, so the direction of the force will be in this direction, whereas the South Pole of this bar magnet will actually attract the North Pole, right? And that is the reason why they have got equal but opposite like pole strengths, and this is the reason why a bar magnet, this bar magnet is also known as a magnetic dipole, right? Now we are going to look at what would be the magnetic flux density at this point, obviously which is on the axial line. The axial line actually indicates that this point is lying on this over here on the axial line, right? On the straight line. If we are going to join the South Pole and the North Pole, we will see that this line actually is, these two lines, they are actually making 180 degree over here, right? Now say for example, as like it is assumed that over here it is the North Pole, so the magnetic flux density at this point due to the North Pole will be in this direction. Say for example we take it as on this direction, this is the magnetic flux density due to the North Pole of this magnetic dipole, right? And if over here there is the North Pole, this South Pole will actually attract it on this direction. So we may say that the magnetic flux density will be in this direction for the South Pole. So in this over here we could find out that actually the Bn and the Bs, they are opposite in direction, right? Now if we do actually imagine this bar magnet as a point object, then we know that as per the laws of center of gravity or the center of mass, we will take the central position over here and we shall measure the distance of this point from the central position. So let this distance be small r, right? And as was indicated earlier, we are now going to take the length of this bar magnet or the length of this magnetic dipole as equal to 2L, which means that from the central point it will be L for the North Pole, and the same applies the L distance of the central point to the South Pole, right? So actually now the distance, say for example the distance of this point from the North Pole will basically be equals to R minus L. So this particular distance we can write it as R minus L. And what will be the distance of this point to the South Pole? It will be simply equal to this one is R plus another L. So this will be R plus L, right? So as per the inverse law, which we have been seeing in the previous lecture, now we could find out the value of Bn as well as the value of Bs. So the value of this Bn will simply be equals to mu naught divided by 4 pi multiplied by m, right, divided by, now what is the distance of separation between them? The distance of separation between this point and the North Pole is equals to R minus L. Right? And as per the inverse square law, this will be R minus L whole square. Now, the value of this Bs will simply be equal to mu naught divided by 4 pi multiplied by the pole strength simply equals to the small m over for the South Pole as well, m divided by R plus L. The distance of separation is R plus L whole square. This is true when in the scenario we have taken the assumption that at this point the North Pole is present and at the same time the pole strength at this point is basically equal to unity. That is the reason why we have kept over here as M and M, because we know that at any point the B or the magnetic flux density will be equal to the multiplication of the pole strength at the 2 points. So the pole strength at the North Pole is equals to small m and the pole strength at this point is equals to unity of 1. So it is m multiplied by 1 will be equals to 1. The same applies for the Bs. Now as we could see that over here the Bn and Bs are actually making 180 degree between them. So we can go for the vector addition of Bn and Bs, where obviously we will see that the direction of Bn is completely reversed to that of the direction of Bs, right? So for the vector addition at this point of Bn and Bs, we can simply write that the total or the resultant magnetic flux at this point will simply be equals to Bn minus Bs. Obviously you can take for Bs minus Bn, the final value should come as negative, which means that first of all if you are taking Bs minus Bn, which means you are assuming that the resultant force is on this side. But if your value after the total calculation it comes out to be the negative, which indicates that the direction would be just the reverse of what it has been assumed. Okay? So for this time being we are taking the Vn minus Vs. We shall be like understanding that why we are taking Vn minus Vs and not Vs minus Vn for the simplicity after we deduce it. So the resultant V will simply be equals to Vn minus Vs, which simply is equals to, if we do take this mu naught divided by 4 pi multiplied by m as common, obviously we can write it as mu naught multiplied by m divided by 4 pi. Now within bracket Bn minus Bs, which means that 1 divided by r minus l whole square minus 1 divided by r plus l whole square. So it will be 1 divided by r minus l whole square minus, because this is Bn minus Bs, 1 divided by r plus l whole square. So we would be finding out that this will simply be equals to mu naught multiplied by m divided by 4 pi multiplied by, let us check this r minus l whole square and multiplied by r plus l whole square as the denominator. R minus l whole square multiplied by r plus l whole square, and over here it should look like r plus l whole square minus of r minus l whole square. Right? So we can write the resultant V as equals to mu naught m divided by 4 pi multiplied by r minus l whole square multiplied by r plus l whole square. This will be r square plus l square plus 2rl minus r square minus l square plus 2rl. Right? So we can now see over here that we can actually cancel out this r square and negative of r square with again l square with the negative of l square. So the next step what we can write is mu naught multiplied by m divided by 4 pi multiplied by over here, this is C2RL plus 2RL, this will be simply equals to 4RL divided by, we can write it as R minus L whole square multiplied by R plus L whole square. Right? Now, if we do take likewise that now the resultant V will be equals to mu naught divided by 4 pi multiplied by 2ml multiplied by, we have taken 2ml, so the remaining is 2r multiplied by 2r divided by r minus l whole square multiplied by r plus l whole square. And this particular, like this expression of 2ml, we have seen in the previous lecture that the multiplication of the pole strength along with the length of this magnetic dipole, or say the bar magnet, will be equals to the magnetic dipole moment for this magnetic dipole, right? Now what is the length? 2L multiplied by M. So 2mL will be the magnetic dipole moment for this magnetic dipole. See, this is 2mL. So we can simply write, as we know, that the magnetic dipole moment is equals to 2L multiplied by M. We can write this as capital M. So hence we can write the resultant magnetic force. Well, resultant magnetic flux density at this particular point will be equal to mu naught. This is 2R. So 2 mu naught divided by 4 pi, let us take it as 2 multiplied by capital MR, because this is R, 2 and M, divided by R minus L whole square multiplied by R plus L whole square. So indeed we have deduced the expression for the resultant magnetic flux density at this point due to this magnetic dipole. Now, is it coming in negative? No, it is coming in positive. Why? Because we have taken Bn minus Bs. So our assumption is correct that the Bn is actually greater than Bs. That is the reason why this is coming in positive. So the actual B will be in this direction. The resultant B. Now, what made us think that, okay, Bn might win over Bs? Simple. As we know that actually this magnetic flux density is the inverse square law, which means that if the distance increases, this B will actually decrease, right? And over here we can see that the distance of this B, for the Bn, the distance is only this much, whereas for the Bs to happen, the distance is so large. So the distance increases for Bs, which actually means that Bs would be smaller as compared to Bn, right? So let it whatever be, if this is a point and we wish to find out the magnetic flux density, we shall just look at what is over here. The magnetic flux density due to this point, this pole will simply win, because the distance over here is lesser as compared to the total distance of the other pole, right? This is the basic funda of this, say, the axial line. Now in many of the cases it is being seen that this point is very, very far away and this R is actually very, very greater than this 2L or this L, right? So if it is being found out that this R is basically very, very larger as compared to L, then obviously we can write B as equals to mu naught divided by 4 pi multiplied by 2mr divided by, we can omit this L, because 1 million subtracted by, say for example, 0.1, that will be simply very, very near to 1 million, right? So we can write it as R square. Again, putting L as 0, we can write it as R square. So we can observe that the R in the numerator will cancel out this 1R in the denominator, which actually means that when R is very, very greater than L, the resultant magnetic flux density at this point will simply be equals to mu naught divided by 4 pi multiplied by, this will be capital M. This will not be the pole strength, but actually the magnetic dipole moment. So this will be capital M. So over here we can write mu naught divided by 4 pi multiplied by 2 capital M divided by R cube. R square multiplied by R, it will give simply as R cube. So we have also found out the expression for the resultant magnetic flux density at a point which is lying on the coaxial line due to a bar magnet or a magnetic dipole when this R is very, very greater than this L. Right? Now in the subsequent lecture we shall be discussing about this magnetic flux density on the perpendicular bisector of a bar magnet or a magnetic dipole. Thank you.